So we're back again in 3.5, and on page 53 of 3.5, there's an opportunity for you to take a look at two example problems from the text. And so what I'm going to do is, I'm actually not going to do these in the video, but instead I'm going to ask that you guys complete these, and we'll take a look at these in class. So I will post later on the work showing these solved, the solutions for these solved. But for right now, what I'd like you to do is just take a moment and complete numbers 1 and 3. And both of these are related to the ballad of the repeating eigenvalue. And so being able to answer these questions will kind of show that you know what's going on up to this point. So if you haven't done that already, just hit the pause button and do that for right now and see if you can answer those questions. So the continuation of this video on page 54 shows us kind of recapping or recapitulating what's been going on up to this point. So up to this point, we've talked about systems with two straight line solutions, very straightforward straight line solutions like these two here. And in this case, you're looking at everything moving along the straight line solutions towards the origin, which means that we would consider the origin to be a sink. Hey, I got it right that time. But they also seem to be guided by the straight line solutions themselves. So in fact, it almost seems like if you were to kind of number these, and if I'm just going to call this one number 1 and this one number 2, and if you were to look at these two straight line solutions, you can see some interesting situations. You can see that if you're kind of floating out here in space, it's this straight line solution number 1 that seems to have the biggest impact on the movement of our particular solutions. And so I would say, in fact, straight line solution number 1 seems to be more influential on the phase plane. And what does that mean? Well, if straight line solution number 1 is more influential, then that means lambda that's associated with straight line solution number 1, its magnitude must be greater than the straight line solution associated with eigenvalue number 2. Right? And we know that's the case. Not only do we know that the magnitude of lambda 1 is bigger than lambda 2, but since everything's headed in towards the origin, that we know that both of these have to be negative. So not only do we know that the magnitude of lambda 1 is bigger than the magnitude of lambda 2, but we know that lambda 1 must be more negative than lambda 2. Both of them have to be less than 0, but lambda 1 is much less than 0. The second thing that we wound up dealing with was, well, what happens if you have imaginary eigenvalues? And so a complex eigenvalue with an imaginary part was the next part. This is what we dealt with in 3.4. And so in this case, you can see everything's kind of spiraling in towards the center. And so we call this a spiral sink. And the eigenvalues for this situation would have to be something like lambda equals alpha plus beta times I, right? That's got to be the form of our eigenvalue. And since we know that it's spiraling inward towards the center, that means that alpha must be less than 0. Alpha, the real number alpha, has to be smaller than 0 because we're talking about spiraling inward. That's what the alpha determines. And if I want to know how quickly this thing is spiraling in, the period of the spiraling, I can get that by taking a look at beta. I can say 2 pi over beta is exactly what's equal to my period of spiral. Now, what's also kind of interesting is I can go one step further and I can say, take a look at an initial condition. If I take a look at an initial condition like this guy right there, what's happening instantly at the moment that I start on the curve, right at that point right there, what's happening to my x of t and what's happening to my y of t? So at the initial condition here, the x of t is getting smaller, more negative. and the y of t is getting more positive. So x of t is getting more negative, while y of t is getting more positive. So x is going this way, while y is going this way. And if you resolve those two vectors, you can see that counterclockwise spiraling is telling us, we can see that based on how the x and y change over time. So this counterclockwise spiral is evident in, I'm not going to say the, I'm going to say any particular solution. X of t and y of t. Right? You can tell what's going on based on the relationship between these two paths. Just say that. So you can tell based on the relationship between x of t and y of t. At that point right there, what must be happening? You can tell that it's got to be a clockwise spiral because of the way x of t and y of t are behaving. And so last but not least, the third situation on this page, we're talking about systems that have only straight line solutions. So repeated eigenvalues, right? Only straight line solutions means you've got one straight line solution and that's it, only one. So it's almost like everything else kind of gets stuck, gets caught by the fact that there's only one straight line solution. And so here, we can't say much about what's going on, except we can say that lambda 1 equals lambda 2, and that they're both, because you've got the center is a sink in this case, you know that both of these are less than 0. So we can't say a whole lot more than that. And so the center is a sink, or the origin is a sink. So just by taking a look at what's going on with the eigenvalue, we can learn an awful lot about what's going on the phase plane. So we have two more special cases to end this section, and we'll do that in another video.